Okay, so I guess I'll start with announcements. Number one, I mean, you saw my email probably. Sorry about the typo. I mean, it's pretty obvious there was one because of how many people were asking me. So what essentially happened was as I was making my solutions, I made an algebra mistake, and then I was in a bit of a hurry because I was like, oh, I gotta get to class, and then I didn't double check, and then I just wrote down. I was like, this is what I got, so that's what you should get to. Which means if you got it down to that, it means you almost guaranteed made the same algebra mistake I made probably, or you just were going through it and you just kind of forced it because you were like, well, that's what he said I should get. That's not your fault. That's my fault, so I won't penalize you for it. If you made a logical error going down there, I'll point out what it was. I'll be like, hey, this isn't, but you still, did what you were supposed to get to what I want, which ultimately boils down to, hey, probably everyone's getting 5 out of 5 on that one. Unless you didn't get to that or what it's supposed to be and made logical errors. That's when it's like, okay, I'll probably have to take marks off for that because then it's neither mistake and it's not following my instructions even though they were wrong, and it's not getting to the right one from talking to me. So then at that point I'd be like, well, okay, it's neither. So yeah, I just wanted to say I made the mistake, so I'm not going to penalize you for my mistake, which is always a good thing. So I kind of mentioned too, I don't think anyone did, but if you had already handed it, I was like, don't redo it. You don't have to redo it. It's fine. I don't think anyone redid it. On that note, though, there is what I call the chapter review assignment. It's posted now. It's due this Saturday. It's only 3 questions.
Like the quiz?
Huh?
Like the quiz?
Pretty similar to that. I mean, I don't want to say it's harder, because it's not really. The first one is making some truth tables. The second question is doing some simplified. I double checked my answer. I swear, if that one also is wrong, I'm gonna flip a table. Because it should be good this time. I even typed it in the Wolfram Alpha, and it agreed, so it should be good. And then the third one is there's like this online sort of logic gate simulator that you can play with, and then I just have you play with that. So on Wednesday, when we're going into our lab, we'll be like, hey, here's a demo of it, how to use it. I mean, it's pretty straightforward. Most people just figure it out. But it's not really fair for me to say, hey, use this website and then never talk about it. So I'll give you a quick demo of it on Wednesday when we have time. And then that's also a good time because I'll be at the computer. If you haven't yet, I'll show you Wolfram Alpha, and maybe I'll prep some exercises. I'll be like, hey, let's ask ChatGPT to do this math problem. And then, well, I'm going to be selecting them so that it's bad at it, which is maybe not fair, but also it's bad at most math problems. Like if you have to do simple algebra, it messes it up, because it turns out if you look up something online about math, most of the things that a large language model could learn on are people asking, how do I do this, and getting wrong answers. So if you train yourself on that data set, you're going to give wrong answers. So anyway, I'll prepare some that, like, one of the common ones I've seen is students will try to build a truth table with ChatGPT, and it gives a different answer every time. It can't really do them very well. So then I could show you that, and then we could go to Wolfram Alpha and be like, see, this is a better tool for the job. Yada yada yada. So I might as well show you the tech. I don't think I have any other. Oh yeah, right. What groups you're in. That thing is due on Monday, I think the 30th. All that's going to happen is when it's due is if you haven't submitted it, it just goes away. And then you can email me if your group changes, or if you're like, oh, I forgot, here's what I'm working by myself, or we're working together, or whatever. And if you still forget to do that, that's fine. If you just submit your first group project and you didn't tell me, I'll figure it out. So I'm like, I'm not gonna be mad or well, hold on, I'll be annoyed, but I won't penalize you or anything like that. So if you forget to do it, don't worry about it. But I imagine a lot of you already have groups of people that you work with, so it's probably pretty easy to fill that out if you just sit down and do it. Okay, so we'll just jump straight into it. So we started our conversation about logic, and so in calculus, as an example, the most common question I get from students, honestly, well, the most common question is, I don't know how to do this, which is fair. The second most common is, why do I care about learning this? And in calculus, I don't know, man. Like, you say, why do I need to know the limit definition of a derivative? You don't, honestly, you don't. We teach it to you because learning the hard way is valuable sometimes, I guess. But that's calculus. There's a broad group of people who take calculus for any number of reasons, right? I don't know if you're going to be a math major or if you're just in like taking it as an option. I don't know. This course, though, is for computer programming students. So you're all in a cohort. You're all doing the same thing. So unlike calculus, where when I'm asked, what's this, when am I going to need this? And my answer is, I don't know, whatever. That's a bad answer in this course, right? Because if you say, Travis, when am I ever going to need this? And my answer is, you won't, then you could be like, then why are you talking about it? And I'd be like, that's a fair point. Why am I talking about it? So set theory. So logical operators is an example. I mentioned circuits are built out of logic gates. So computers, we can explain binary with it. We can, logical statements in programming languages are built out of that. So, there's some connection there. Set theory. Why do we care about it? Well, one is kind of logic is the building block that we use to build sets, which then we use to talk about all math. So we kind of just need to make sure we're all on the same page with the language we use with sets. There's a lot of common notation and language that we use with them. So I just want to make sure that we all know what we're talking about. But there is actually a computer science reason to care about sets, because you're all in the databases course, right? No? Yeah. So understanding sets and union and intersection and Venn diagrams and stuff like that will help you do joins. If you're sitting there and you're like, okay, I've got table A and I want to join it to table B, is it an inner join, an outer join, a left join, a right join? I don't know. If you understand set theory a little bit, it makes it easier to determine which one you need to do, right? It's if you understand set theory, you won't even ask that question. It won't even be a question of which one do I need, because you'll just instinctively know, oh, this is obviously a left join, right? So it's helpful in that sense. Set theory comes up a lot in databases, is kind of the point. So that's the why do we care about sets for programming. Like I'm kind of saying, though, for our purposes for math, just like logic, they're kind of interesting in their own right, because we can build like a sort of algebra out of them and talk about properties and that sort of thing. And that's a study on its own. But for us, we will mostly need set theory to make sure we're all on the same page for notation. Because there is kind of a lot of it. So and then we can just sort of generalize when we talk about what we need. So let's start with, what is a set? Well, any guesses? What is a set? Like just you ask like a high schooler or something, like, what's a set?
Group of something?
Yeah, exactly, right? Like that just, like, it's a collection of stuff, right? It's just, you just take all the stuff, put it together, that's a set. So a set is a collection of objects. It can be whatever you want. We use curly brackets to indicate a set, which, so you've taken the Python course. That's not a surprise because a set in Python is indicated with curly brackets. The Python set is literally a math set. It has all the same properties, such as it can't have duplicate elements, it's unordered, that sort of stuff, right? It matches the same as a math set. So we usually use capital letters for sets. There's nothing wrong with any symbol you want. It's just this is a convention. So a set would be like 1, 2, 3, Travis. Right? It's a collection of stuff, right? We got some numbers in there, and then I'm in there because I don't know, why not? So obviously when we're talking about sets, we usually restrict ourselves to the same data types or objects or something like that. So, you know, combining people with sets probably not something you would do in a normal set, but there's technically in the definition of a set nothing stopping you from doing it, at least with this definition. Okay, so any object or any specific object in a set is called a member of the set or an element. And when we're talking about belonging to a set, we have a specific kind of notation for it. Sort of shorthand to indicate whether or not something is in a set. So the notation, it's essentially a funny looking E, means belongs to or in when we write it down, or element of. There's lots of different phrases for it, but in terms of how we actually write it, it'll make sense why it means that. So we look at this set here. 1, funny E A. This just means 1 belongs to A. 1 is an element of A. 1 is in A. So we read that. I read it this way anyway, is in A. Right? Because in is just the shortest way to read it. All of these are correct though. Conversely, 4 is not in A. How do we indicate not? Well, same way we do with equals in math, we just put a slash through it. This is read as 4 is not in A, right? This is, of all of the things we talk about in set theory, of all of the notations, this is the big one because eventually I'm just going to use it all the time without even a slight indication of what it is. So this is the one where it's like, put this on a post-it note, make sure you know what this notation means because we're going to start, we'll use it a lot. Now, this is sort of the I'm a mathematician, which shockingly means I'm a total nerd. I love this stuff. So that means don't write this down, but this definition of a set, which mathematicians would often call the naive one, because I mean that's like if someone asked me what's a set, I would be like, well, yeah, it's a collection of stuff, right? It's just a bunch of objects. That's actually not a good definition for a set mathematically, because you can run into a lot of problems. There's something called Russell's paradox. So if you also have math brainworms and want to look it up, you can read about why we don't define it this way. And it actually, I think he wrote a paper about this in I think the 50s, and it like completely blew up mathematics, because he said, hey, what about this, you guys? And everyone was like, uh-oh, we didn't think of that. That breaks a lot of stuff. We need to be more formal, and we need to come up with better rules. So what he said was, all right, set is a collection of stuff. So then define a set to be all of the sets that are members of themselves. So, it would be like A is in A. right? So, I mean, we just said a set is a collection of stuff. So, sure, it can contain itself, right? Like, why not, right? It's just stuff. So, self-referential definition, that's totally fine. It turns out, no, that's actually not fine, because then you get that anything in that set has to be a member of itself, but it also can never be a member of itself, and it's a paradox, right? It doesn't make any sense. So again, this is nerd stuff. This is relatively recent. It was in the 50s that we were like, hey, we have to reinvent math. And there's some really funny controversies about it. Like it's a bunch of nerds arguing over beers, essentially. But that makes it kind of funny. Except they're really heated about it. Actually, the just to say what it is, it's whether or not set theory includes something called the axiom of choice or not is like controversial. Think of it like you got a bunch of programmers in a room, and everyone's like, my favorite language is this, and it turns into a whole argument about everyone being like, no, that's why that language sucks. This one's the better one. This is why Python's the best. And someone's like, no, this is why Java's the best, and so on. Like it's basically that. So I'm sure you've already had experiences with that. Anyway, moving along, there are some common sets that come up often. So we gave them symbols. Just to really shorthand them so it's easy to, reference these very common sets. So the first one, it's N with a funny line next to it. This is called Blackboard font if you're looking at typesetting it. Which actually, sorry, this is related to quiz 2. This happened. A number of students submitted using, I don't know what it is. It's like LaTeX, but not. Someone mentioned the name of it, and I was like, I've never heard of it, but it looks like LaTeX, so I can read it. But then I realized you were giving me essentially, if I said, give me your website, and you gave me all the HTML tags, but didn't give me, it wasn't rendered, I'd be like, this is not what I mean. So don't give me that. Take the extra step and render it as a PDF or PostScript. There's no reason not to. You're making me parse through essentially garbage. I can read LaTeX, to be clear. I can read it just fine, but you're making me do extra work. So I didn't penalize anyone this time, but I did say hey, if you just render it to PDF next time. If you have it written in this format, you very easily can export it to a PDF. So please just do that extra step for me instead of making me do it for you. So that's anyway. People who know how to do that will recognize this symbol because it's in typesetting. Anyway, this is the natural numbers. A set of natural numbers. Or whole numbers. Or counting numbers. So these are usually the first numbers we run into, when we first learn to count. 1, 2, 3, 4, that sort of stuff. So there is one sort of arbitrary thing here. And I say arbitrary because this set here, natural numbers, does it include 0? Yes or no?
Yes.
Does anyone think no? Did anyone learn no for that? Okay, well that's convenient, but generally speaking, it's kind of divisive because it's arbitrary, right? Whether or not it includes 1 to 0. For programming, we should obviously include 0, right? Because we index from 0, so we're going to include 0 to make our lives easier. But sometimes it's more convenient when you start at 1, like when we're talking about induction or iteration through algorithms on a whiteboard or something like that. It's more convenient to index with 1. So for us, this set includes 0. So that means this is 0, 1, 2, 3, 4, and so on. Right? It's just all the counting numbers just collected together. Now, there are infinitely many of these, right? They go on forever. So that's what this ... is indicating here. It's saying, hey, this pattern that we've started, keep going forever. Don't stop, right? So that's what we're saying here. We're saying 0, 1, 2, 3, 4, and keep going with this pattern. Okay, so the next set that we talk about a lot is this funny Z. It's Z because you might be thinking, okay, so this is natural numbers. This is going to be the integers. Why is it a Z? Because the German word for integer starts with a Z. And a lot of this notation was developed in Germany, so that's why it's a Z. I do not remember what the German word for integer is, but it starts with a Z. So this is the integers. So these are the positive and negative whole numbers. I promise none of these sets are going to be anything like there's not going to be a twist here. They're what you remember. So this is, we're going to start at 0, 1, 2, 3, 4, and so on. But then we also have the negative numbers. And so on, right? So this is saying, hey, keep going in this direction, but also keep going in that direction forever. The next set that we have is a Q for quotient, or probably another German word for rational number. This is the rational numbers, or fractions. So it's a lot harder to sort of write out in a list form for these. So we have to come up with sort of a more convenient notation, but this is all numbers of the form A over B, where, and this is where I'm gonna start using this notation. So A is in the integers, or A is an integer. That's what this means. And also B is an integer, right? So we're saying fractions, right? It's an integer over top of an integer, right? Have I defined this correctly? Does this seem right? If we think of every fraction ever, is this all of them, or is there a problem? So what numbers are included in the integers?
0.
Yeah. So this tells us that we could have 0 over 0 as a fraction, which no, we can't. That's not a valid fraction. So we need an extra condition here. B is not 0. And now we've got the fractions, right? We don't want to have a fraction with 0 as the denominator. Okay, the last one is sort of that when people are talking about numbers, this is usually what they mean. Unless we're talking about like array indices or something, then we obviously mean this. But if someone just said, hey, give me a number, I mean, most of the time people will give an integer, but if I said give me a number and you said square root of 2, that's technically a number. This is real numbers, R. So this is, for all intents and purposes, every number. So this is basically every number, rational and irrational. So rational numbers are fractions, right? They're things of the form A over B, where B is not 0. Another way to think about them is in terms of decimals. So these would be the repeating decimals, right? At some point you have it either terminates or repeats, right? So 0.5, right? It's stopped. 0.333 forever, it's repeating, right? It's 3 repeating. So that's what these are. Irrational numbers are non-repeating, right? There's no pattern there at all. So this includes such favorites as square root of 2, pi, which is everyone should at least be vaguely familiar with from maybe not high school if you took 30-2, but like pop culture, right? People talk about pi a lot. Memorizing digits of pi is a common nerd joke. There's also this one here, Euler's constant E. It's another important mathematical constant. It's just another number. But the point is, for all 3 of these, they have the same thing in common. They have a non-repeating decimal expansion, which, you know, for computing, these easy to store. These, well, at some point we have to decide when to stop because they don't repeat. So how much precision do we want? We have to decide. So irrational numbers are problematic. And actually, some really bad rational numbers are also problematic for the same reason, because we have limited storage space, and eventually that decimal doesn't repeat until like 100,000 spaces.
Sorry, what does the E stand for?
That is Euler's constant. It is 1.71 something. It's called the exponential function, generally speaking, when we talk about e to the x. What you need to know is it's just another number, right? It's just a fancy number like pi. That's all that matters about it. Okay, so these are, generally speaking, the ones that we would care about in math. There are others, like there's the complex numbers, which have the imaginary unit, right? That's that I. That maybe you've heard about if you took very specific types of physics or electrical engineering, stuff like that. That's where it comes up. Or on top of complex numbers, there's something called Hamiltonians, which that's like very, 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 very hyper-specific physics where you would run into that. So you can keep going, but like these are the ones that we actually generally care about. Now, fortunately, there is a decent amount of overlap between logic and sets. There is a lot of overlap between logic and sets. So this is sort of the mathematician's creed, work smarter, not harder, right? So if we can sort of steal stuff from logic to build stuff for sets, that's convenient, right? We can save some effort. We don't have to redefine some stuff, right? If we can define it in terms of the logic we already talked about, then that would be good. So one of the most common ways that we actually use logic sort of implicitly in sets is in defining them. So if A is a set, then the formula P of X X is in A is true when X is in A and false when X is not in A. So what that means is we can essentially take logical expressions and use them for sets, right? So the most common way to define sets is either as just a list of objects if it's finite, or the following notations, which I'm going to write down the notation and then I'll explain what it means. I'm going to use a different letter here. So this is the notation that's commonly used. So what does this mean? Well, we've got the curly brackets here. That means we're talking about a set, right? Curly brackets means set in math. We got this logical expression here. But then we've got this extra symbol here, and they're the same. It's just this looks a little nicer when you're typing it. This is easier to distinguish on a whiteboard. So I'll gravitate towards this one when I write it, but in my notes it'll use this one. They're the same thing. But what this means, this symbol, there's two ways to read it, is such that or where. So what that means is this right here is read as all the x's such that q of x is true, right? Where this is some logical statement, right? So when I write it in this formal way, it's really cumbersome, right? So examples are usually instructive here. So let's take a look at what I mean and how this appears, and then when you see it, you'll be like, oh yeah, okay, I've seen that notation before. It might have been a really long time ago, but you've probably seen it. So let's consider the set. So we're going to write it like this: x such that this, right? So we look, this piece right here is q of x, right? It's either true or false depending on what x is, right? Either x is bigger than or equal to 0 or it's not. If it is bigger than or equal to 0, we're saying let's include it in the set, right? This is the condition on our set. So we read this as x such that x bigger than or equal to 0. Or, better, this is a bit more down-to-earth language, all the x where x is bigger than or equal to 0, right? That's what this is saying. So, well, I mean, we have another word for that, of course. That's the natural numbers. If x is an integer or something like that, right? If it's a real number, then this isn't the case, but you know, this is another way of writing that same set, right? So it takes some getting used to with this notation of like reading it out loud. But the most helpful thing is to literally read it out loud or like write it down and just say, okay, this right here, this first part, all the x such that, right? That's what this means. All the x such that this is true, right? Or you could also say, another way of saying it, all the x that satisfy x bigger than or equal to 0. So lots of different ways to sort of read that, but they all mean the same thing, right? Give me all of the things that satisfy that condition, right? Okay, so in this case, it's positive numbers, right? Including 0. So let's think about this set again. So this thing here, one, two, three, four, and so on. So I have that and so on there, right? So I just want to talk about this real quick, because when do you write that? Well, when you have some kind of pattern that just goes on forever, right? But when do you write it in the sense of how many do I write down, right? I did 0, 1, 2, 3, 4 here, and then I did ... But you know, you could just say 0, okay, it's terribly unhelpful, right? What's the pattern here? Or I could say 1, right? Is this odd numbers? Is it prime numbers? Well, no, it can't be prime numbers. Is it, how about this? 16, 25, 36. So they both start with 1, right? But they're different. So the general rule here is, when do you stop writing? When it's clear, right? And sometimes that could be you have to write a lot, right? Because that's fine, right? Until you see the pattern. But this sort of is a documentation thing, right? If you wrote this and then walked away from it for a week or two, could you come back to it and look, okay, I can see the pattern from that, right? If you can, then it's enough, and you can write the ... That's fine. But if you look at it in 2 weeks and you're like, I don't know what the pattern is, and that means you didn't write enough numbers, and you probably should. So this is odd numbers, right? This one here, what does this one look like? I mean, it's fine if you can't spot it, but just, yeah, it's squares, right? So this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, so on. But you can see if I wrote 1, 4, that might not be enough, right? 1, 9, 1, 4, 9. Maybe some people can spot it, maybe some people can't, and that's totally okay, right? If you need this many to spot it, you should write that many, right? So it's up to you on when to do that. But there is something else you can do. You can explicitly write the pattern sometimes. And this is, so this is kind of what I mean. 1, 3, 5, 7, ... When I said natural numbers sometimes include 0 and sometimes they don't. So when we're actually literally counting on a board as human beings, we start at 1. So that's the first position, right? Second, third, fourth position, right? First number, second number, third number, fourth number. So what you can do is you can say, well, at the position K or I, whichever you'd like, this is 2K minus 1, and then more dots. So what we've done is we've very explicitly written down what is our pattern. Well, at index K, it's this, right? So at 4, right, index 4, 2 times 4 is 8, minus 1 is 7. Well, that matches this, right? Index 15, 2 times 15 is 30, minus 1 is 29. So when this is 15, we know it's 29, right? So this is, if you've already done Python, then this is just array notation, right? It's iterating over an array. That's the index notation here. It's just saying, hey, when we have this index, this is what the pattern is, right? That's all that's saying. So all of those are fine. You can write it explicitly like that if you ever need to. But I would say most people do this because it's usually the patterns are self-explanatory. So we have another important set. It's a 0 with a slash through it. That's the notation we use. And if we think, well, what is a set? We're calling it a collection of stuff, right? It's just it's a collection of objects or whatever, right? A bag of things. Then we have the notion of an empty bag, right? I'm going to the grocery store. Before I actually buy my groceries, my bag is empty, right? But it's still a bag, right? Even though it has nothing in it. So this is the same idea. We have an empty set, right? And this is the notation we use for it. So this is just a set with nothing in it. The set has no objects at all. And this notation, we've chosen it kind of deliberately, like it's almost a 0. The slash through it is just to distinguish it from 0. But the empty set for the operations we define behaves an awful lot like 0. So that's why we chose this notation. It functionally behaves that way. Okay. So let's turn to our logical operators. From before to try and get set operations. And when we say operations, we just mean a way to get sets, new sets from old sets, right? That's all an operation does. It takes two numbers and makes a new number. This is going to take two sets and make a new set, or one set and make a new set. So the complement is the first one we'll define. Complement of a set is given by. So the notation is we write down the set and then we put a C at the top of it. This is not an exponent, it's just a symbol to mean complement. So what the complement is, it's all the stuff that is not in A. So using this notation, it's all the X so that, such that, where, all the X where X is not in A. So in other words, this is all X where X is not in A. So it's just everything outside of it. Right? So we take a look at this one right here that we defined. So this set is the odd numbers, right? Let's call this set B. So now we have this complement operator. Well, what's the complement of this thing? So right here, it says all of the odd numbers. So what's the complement of the odd numbers? Yep, exactly, right? We think, what is this defined to be? It's all the stuff, all the X's that are not in our set. So what's in here? Odd numbers. So this thing is all the stuff that is not in here, which would be all the even numbers, right? It's either an even number or an odd number. So this is odd. So usually the complement is relatively straightforward to find because it's, you know what A is, so it's just the stuff that's not in A, right? You just take everything that isn't in there. So usually you're comparing it to a bigger list, like in this case, well, it's infinite, but we looked at this and we're like, okay, 1, 3, 5, 7. So if I were writing it down, I'd be like, okay, not 1, 2 is missing, so I would write it down. 4, 6, 8, and then I'd be like, okay, it's even numbers, right? So that's generally complement is not too bad of an operation. Okay, so that one's not too bad. But so this corresponds to negation, right? This is X is not in A. You could even say, if you really wanted to, right? Like the negation of being in a set. But there's that natural correspondence, right? So if B is another set, then the intersection denoted a cap B or a funny upside down U, whatever you want to call it. So this is going to be all of the objects, all of the x's, such that x belongs to A and x belongs to B. So see, we're essentially cheating here, right? We defined a new operation on sets, right? These are sets. And really all we did was we used the logical operator for and, right? And we're even so lazy that this is like this triangle, and we just smoothed it over to get a new operation, right? So in words, because I think it's important to just get practice taking these sets and just reading them out. So in words, how do I want to say this? All the elements x where x is in A and x is in B simultaneously. And I'm just drawing that distinction that by and in this case, we mean it's in both of them at the same time, right? Just making that very, very upfront. Okay, similarly, we use the and operator here, so let's cheat and do the same thing with the or operator. We also have set union A Q B for union. Same thing, except we do an or. So let's read this out. This is all the x that satisfy x is in A or x is in B. Right? So it's all the stuff that is either in A or it's in B. Right? That's what this means. This is or. It's either this is true or this is true. Right? Either one of those is true. So in words, all the elements where x is in, I'm going to say where either x is in A or x is in B. Right? Either one. So the most common mistake that students make with these operations is not. It actually has nothing to do with the operations here. It has to do with mixing the symbols up. Because so intersection, usually they students know the idea here. This corresponds to and, right? It's and. We even often say A and B for sets. So they know, okay, one of them corresponds to and, one of them corresponds to or, but you get the symbols mixed up, right? That's that. I'd say the most common mistake is just mixing up the symbols. So it's not even like a conceptual misunderstanding, right? It's the students know what to do with each of them. They just get them mixed up. So in summary, A intersect B, or A and B, means what do my bags have in common? That's the intuitive idea of what this means. And A union B means essentially dump A and B into the same bigger bag. You just combine them together and just say, all right, that's a new one, right? Just dump them all together. Okay, so let's do an example of actually using these operations with like numbers, some like concrete stuff instead of just talking about symbols. And this is everyone's kind of done this stuff at different times in life. Like I've had students where like, yeah, I did that in like 5th grade, and then it's been forever since I've seen it. Some people are like, yeah, I remember doing that in grade 10. I remember doing it in grade 12. It's kind of all over the place. But most people have seen this. Okay, so suppose the universe is the following. So that just means all of the numbers that we're considering, right? So it's not quite every whole number or anything like that. 7, 8, 9, 10. So it's just the numbers 1 through 10, right? So let's let A be the following set. Be careful to copy this down the same. So 1, 3, 4, 5, 7. So that's that. And B is the following set. 1, 2, 4, 7, 8, 9. So let's perform some of these operations on these. So a complement. So this is a wake-up check, I guess. What's in a complement? So remember, this is the stuff that is not in A. 2, 6, 8, 9, 10. Yeah. So what we do is we just essentially say, okay, well, what's in A? We got a 1, so I don't write that down. I don't have a 2, so I write that down. Don't write 3, don't write 4, don't write 5, write down 6, don't write 7, 8, and 9 or 10 are written down. Okay, so like I said, the complement, especially like when you know the set, it's just everything outside of it, right? Everything that's not in there. Okay, A intersect B. We think, what do these two things have in common? So what does A intersect B in this case?
1, 4, 7.
Yeah, it's just what do they have in common? They both have a 1, they both have a 4, and they both have a 7, right? Now set union is literally just dump them together. This one we don't even really have to think about. We just literally write them down. So I just look at what's in A. 1, 3, 4, 5, 7. 1, 2, 4, 7, 8, 9. Now there is one extra caveat with sets. Everything in there has to be unique. We don't write duplicates. So that's easy to do too. You just look at it, you say, okay, there's 1. Do I have it again? I do. 3, do I have it again? No. 4, there it is. 5, nope. 7, cross it out, and then we're done, right? So you could write this as, or should write it as 1, 3, 4, 5, 7, 2, 8, 9. No duplicates, again, just like Python sets. We don't have duplicates in sets. Same exact idea. Another important thing here with sets in math, order doesn't matter. With sets, the order in which we write elements doesn't matter. So, this set here is indistinguishable from if I swap the 4 and the 1, right? So like as long as they have the same stuff in them, then we would consider them the same. I mean, again, the intuition, this makes sense. You got a bag of groceries. My friend bought the same groceries. They're obviously just going to be shuffled, like it's a different order for how the groceries are packed in the bag, but it's the same groceries, right? Same stuff. So we don't care about the order in which we do things in sets. Okay. We have another very common way of representing. Sorry, yeah.
Sorry. A union B, why two is not it?
It is.
Okay, sorry.
I mean, it's good to check because I might have forgot it. So often with sets, we visualize them with everyone's favorite Venn diagrams. So if there was something from school that you really remembered about set theory, it's going to be these. Maybe this notation, you've seen it, but it wasn't really emphasized. It's not that important. Venn diagrams is something that you would have seen. So they look like this. God, what is the marker? Or either it's the marker or it's the eraser. I don't really know which. So stuff like this, right? Where we're gonna fill in these circles. This is the stuff in A, the stuff in B, the stuff that they have in common, right? With a 3-set Venn diagram, like that. A, B, C, same thing. We just fill them in, right? So let's actually take a look at our previous example here. So what were our sets? Well, I literally just erased them. But we had wait, no. I'm drawing a box around the wrong one. This is the one I want to box around. Because we had 2 sets. So we have this sort of universe, right? Everything here sits inside this box, right? Either it's in A, B, or not in either of them, in which case it sits outside of it. So we can fill these in, right? So the most common way to fill stuff in here is I just write down what's in A. 1, 3, 5, 4, 7. Boom. That's everything that's in A. For B, it's 1, 4, 2, 8, 9, and 7. And then we actually have 2 numbers left over, right? 6 and 10. They're in neither of these, so they kind of sit on the outside, right? Now, Venn diagrams are not different from sets. We don't write duplicates, so we just look. There's a 1 and there's a 1. But instead of not writing it, we put it in the middle, right? Because this is what they have in common, right? This middle piece is what's in A and in B, right? They overlap with each other. Same thing with 4, that's in both. 7, that's in both. Now, if you want to clean it up, you could erase the ones you just crossed out to make it look a little nicer, but it doesn't matter, right? It's clear that you crossed them out and they're not in here. Now, with Venn diagrams, though, what we're usually interested in is a more abstract kind of thing, and this is thinking about sometimes thinking about tables in terms of these Venn diagrams is helpful. A, B. We often think of Venn diagrams abstractly. And shade in regions. So as an example, we would say, okay, well, the region of this that I'm interested in is, let's say, this blue part, right? The part I just shaded in. So we can look at that and we can figure out what the set operation is. It's intersection, right? But these come up in terms of joins, right? Like a left join would include the stuff in the left table joined with the right table. So that would often be drawn like this. Right, so it's saying, okay, I want the stuff in the left and the stuff in the middle. But you could also say, I only want the stuff on the right. excluding the stuff in the middle. Right, so thinking of things in terms of these Venn diagrams can kind of just tell you, okay, you know, I've got these two things that are connected in the middle. What do I actually want here? Do I want all the stuff from the left connected on the middle? Do I want all the stuff on the right excluded from the stuff in the middle? Stuff like that, right? Like these Venn diagrams can help you sort of visualize your data a little bit in terms of how it all fits together. Okay, so now we've got some operations here with sets. You know, we can form new ones from old ones. We can do intersection. We can do union. We can complement. But we need to be able to compare them, right? When are they equal? So we need equals. And there's another one that's really useful, the idea of being a subset. So, okay, with these definitions that we've sort of been rocking, well, two sets being equal, when are they equal? Yeah, same stuff, right? Like, I got a bag of groceries, my friend has the same bag, like the same stuff in the bag, we'd say, like, I wouldn't care which one I got at that point, right? They're the same thing. So when they contain the same objects. I'm just gonna say same stuff. Right? That one's pretty sensible. So subset. Now this one's a little weirder. So I'm going to say A is a subset of B if, I'm going to write it in the symbols, but it will make sense when we read it out loud. So, okay, symbols, it's kind of messy and it's a lot. But let's read this. For every choice of X, if X is in A, then X is also in B. Right? That's what this means. This is for every choice of X, right? This symbol right here, in math, we often read it as if, then. So if the first thing is true, then the second thing is also true. So if X is in A, then X is also in B. Right? So it's literally if stuff is in A, then it's also in B. So in terms of Venn diagrams, what does this look like? So we've got A, and then it just sits inside of B, a bigger thing. That's all this is really saying, right? So the notation is, and we're, again, mathematicians are lazy. It's just the same symbol, but now we just rotate it instead, right? We just take the same thing and flip it upside down and rotate it around and get new symbols. The notation is this and means ultimately A sits inside of B, right? It's contained in B. So it just sits inside of the whole thing. So like if B was 1, 2, 3, 4, and A is 1, 2, well, A sits inside of B, right? There is 1, 2 inside of B. So if we drew that as a Venn diagram, 1, 2, 3, 4, this is saying B contains 1, 2, 3, 4. A only contains 1, 2. Now, the most common containment or subset things that we talk about is the following. And it's one that we just sort of intuitively know. So we've got the natural numbers here, counting numbers. These sit inside of the integers, right? Well, that makes sense because what are the integers? It's just this and also the negatives of that, right? It's just the positive of these and the negative of these. So that makes sense. Well, these integers sit inside of the rational numbers. Well, why is that? Well, what is a rational number? It's a over b, where a and b are integers. So a over 1, right? That gives us all the integers, right? Because a is an integer over 1. So that's just going to be all the integers. So, okay, this makes sense. This sits inside of here. And this sits inside of here just by definition, right? Because we said this is all the numbers, right? So everything rational and irrational, well, obviously it contains the rational numbers, right? So most of these kind of make sense, right? This is defined in terms of this. This is partially defined in terms of that. This is also defined in terms of that. So like they sit inside of each other in sort of a natural way. Okay, so I'm going to make you do some math now to cap off the evening. So I'm going to write down a set, and I'm cheating. I'd love to say this is a random example that I made up, but I did it already. So it works. So that's the good news. You don't have to be the guinea pigs here. So let's let you be the same one as before. So the number is 1 through 10. Let's let A be the following. 1, 3, 5, 6. B be the following. And C is this. So we got some sets here. So what we want to do is draw a Venn diagram. And find the following things. A intersects C, A union B, A intersect B union C, A intersect C complement. So this right here, we've got sort of two operations here, right? But still follows the same rules as logic and as anything else. Do the brackets first. So you want to do this stuff in the brackets, and then whatever you get from that, you do the rest. So as sort of a note here, sometimes when you look at an intersection, there's nothing in it, and that's okay. So just as a note, sometimes when you find the intersection of stuff, they have nothing in common. That can happen, right? You can have something that looks like this. So A intersect B is nothing, right? This is actually a concept called disjoint. So we'd say these two sets are disjoint. We don't need to emphasize that too much. I just want to say, hey, it's possible for you to take the intersection of two sets and get nothing, right? So I'm going to let you go on your merry way to do this. At the end, at 7:20 or whatever, I'll write down the answers that I got. And then if you didn't get the same thing, feel free to ask. If you are working through it and you're like, oh, I'm missing something, feel free to ask. That's what I'm here for. This is just like either it's a quick thing to work through, or if you're like, I get it, then you can go home 10 minutes early, I guess.